So today we're going to be talking about the cyclic, extremely stable planar structures with rings of resonance bonds known as aromatic compounds. With these structures, which are usually seen as like benzene, right? You got your generic six-membered ring with pi bonds within it. This increases its stability, right? Since stability increases, reactivity decreases. This makes it such an extremely stable compound that we must use different reagents that haven't been seen before because of the stability. You can't just do terpbutoxide and then expect a normal elimination or substitution reaction to occur. So electrophilic aromatic substitution solves this problem, in which you take one of the ring hydrogens and you can replace it with a halogen, a nitro group, a sulfonic acid group, alkyl or acyl group. So in order to get these reactions to happen, we have to use specific reagents. So in this case, I'm going to use chlorination. I'm going to do chlorination/bromination of benzene. And this is just a fancy way of saying putting Br or Cl on a ring. You use Br2 FeBr3 as one step, and then that will place a bromine on your benzene. So there's 3 steps that every one of these reactions are basically going to take. So I'm going to write out these 3 steps. I'm going to go through one of the mechanisms, like kind of slow the first time. But you'll notice the pattern just repeating over and over, okay? So the first step is that we are going to be creating an electrophile, okay? Second step, electrophile is attacked by benzene. Third step, we regenerate that aromatic ring because you don't want this positive charge right here to just lie around. You know, we want a complete reaction. We want everyone to be happy. We want all octets to be satisfied. So first step is create that electrophile. The Br2, one of the BRs, is going to donate their electrons to this FeBr3, creating this electrophilic bromine right here, okay? So this is our souped up electrophile, as Dr. King likes to call it, and this is what is going to be attacked by benzene, okay? So benzene attacks this bromine. This covalent bond is broken, and the electrons are donated to this electrophilic bromine. The positive charge is gone. FeBr3 and FeBr4, apologies for that. Ooh, even I make mistakes. Let's go. Okay, so FeBr4 becomes a byproduct of our reaction, okay? So essentially that goes off into the solution, but the Br minus comes in the third step. But okay, so back to the second step. So after the souped up electrophile is attacked, we create these resonance structures, which I highly recommend pausing before I show you the resonance structures, okay? Because this is good review, and it's always a good practice to, you know, make sure you got your resonance structures down, because this could be asked on a test question. So here we go. Pi bond goes over to the right. That is then replaced. Positive charge kind of follows. Then we have this pi bond coming down. That comes down here. Positive charge ending up here. And that should be all of the resonance structures. Remember, you don't have to do the exact same order that I did. Just remember how it works, okay? Please, you know, hopefully you understand how resonance structures work. It's great practice. And this is, once again, reiterating that this is a resonance stabilized carbocation that you get from this second step. So even though carbocations are very unstable, since it's resonance stabilized, it allows this reaction to occur in the first place, okay? Because it increases stability of the transition state. Ooh, tongue twister. Okay, so step 3, okay, we regenerate that aromatic ring. The Br minus from this byproduct right here comes down. It doesn't come down. It's just floating in the solution, essentially, or whatever mixture we have. And it comes back, attacks this hydrogen right here, and we regenerate the aromatic ring. Remember, this is an overall E1 elimination reaction. SN1 or E1, the first order reactions, are always going to have a carbocation as this intermediate within the reaction. So when you see that carbocation right here, and we're talking substitution or elimination, you're going to talk about the first order reactions. And that's going to keep track of carbocation rearrangement, carbocation resonance structures, all that good stuff. But these are the three key steps in electrophilic aromatic substitution. Once again, creating electrophile. The electrophile is attacked by the benzene. We regenerate that aromatic ring. Is nitration of benzene. This is where you take benzene, you add nitric acid and sulfuric acid with heat to put on a NO2 to replace one of the hydrogens of the benzene to NO2, nitro group, right? So, you have to first make the electrophile in which the hydroxyl groups oxygen will attack the sulfuric acid's acidic hydrogen, as we see right here. This will create a very unstable compound where you have three formal charges, right? And that's a very unstable compound. You don't want that many charges in one place or one compound. So instead of keeping this together, the compound basically breaks down because the water molecule right here acts as a leaving group in which you dehydrate this overall compound, creating a nitronium ion. As this, we see this oxygen is giving its electrons to this bond with nitrogen to maintain oxygen's octet, and then also we leave this positive charge on the nitrogen, ultimately creating a nitronium ion, right? And everything's good so far. We have created an electrophile that is going to later be attacked by benzene. So, once again, this instability, unstable, right? Having this many formal charges in one small compound is very unfavored. So that's why we have this water molecule act as a leaving group. The oxygen on the other side donate its electrons to then sort of create this elimination process where you break a bond and you create a double bond, okay? So, benzene then attacks this nitronium ion that we have created in the first step. Then you create a resonance stabilized carbocation. As we said before, it's a great way of practicing your resonance structures to just draw this out once or twice so that you are comfortable with this process, okay? So, the nitro group is on there, but you don't want the positively charged carbocation, so you regenerate your aromatic ring, and that is done by the water molecule that recently left, remember from this first step, the dehydration. That water comes back, or your deprotonated acid comes back and gets that hydrogen. This bond is broken and donated to the ring, leaving us with product. Is sulfonation of benzene. You're going to take your benzene and then add fuming sulfuric acid to create a benzene with SO3H, which is sulfonic acid, replacing one of the hydrogens. You're going to create your electrophile, just like all the other steps. Then you're going to take SO3. SO3's oxygen, one of the bonds, is going to attack the hydrogen like so. Then the hydrogen bond is broken. The electrons are donated to the oxygen while the hydrogen is taken. Then you create your electrophile, right? Positive charge, everything's looking good. And this is what is going to be inevitably attacked by benzene once again, right here, right? That results in SO3H with a resonance stabilized carbocation. Remember, when you put this on the test, you're also forgetting the two other resonance structures. So since I've already drawn those resonance structures before, feel free to test yourself if you want, but know that there's two other resonance structures involved. But yeah, so our third step, regenerating the aromatic ring. The deprotonated H2SO4 from the first step can come back, attack the hydrogen, and then cause elimination, resulting in a regenerated aromatic ring. So, the key thing about this reaction is that we are going to be using it as placeholders in synthesis, right? I've highlighted it in the box, right? You use it as a placeholder because it's reversible. You can place SO3H on the ring and then force another substituent onto another position. Alrighty, so the next reaction that we're going to be talking about is Friedel-Crafts alkylation. So we're going to repeat this process of creating an electrophile, and we're going to create this electrophile to alkylate the benzene, right? We're going to add an alkyl chain to the benzene, okay? So you can replace one of the hydrogens. I don't know why I'm talking like this, but but basically you replace one of the hydrogens with an alkyl chain. Now, the difference between this and the other reactions is that depending on what your reagent is, you might create a carbocation or you might just create an electrophile. So if it's a secondary or tertiary alkyl halide, you're going to create a carbocation, okay? That's because the carbocation can be made and stabilized by the other carbons that are donating their electrons to the positively charged carbon. They're not completely donating it, but they are their electron density is being pulled towards the positively charged carbon that stabilizes the positive charge. So that's why secondary, tertiary, you lead to carbocation. Whereas primary, you don't. It's just too unstable. All right, this is from basic OChem. Primary carbocations are just too unstable to be created. So we just create an electrophile that can be attacked later on. So let's attack that electrophile. Depending on, regardless of whether you make a secondary or / tertiary electrophile or a primary, you're gonna get the same result. You're gonna add an alkyl chain to the benzene, but be weary of the fact that when you see carbocations, right, you should be aware of the fact that carbocations are very they can be unpredictable, so when you see carbocation, ask yourself rearrangement. Is something being rearranged? So you need to watch out for that. So in this case, we have a tertiary carbocation, and it doesn't matter if something shifts because tertiary in this scenario is the most stable, so we don't have to worry about it. So you create the benzene attacks, and then you regenerate the aromatic ring. I'm not going to go through that whole process again, but basically, the benzene attacks, regenerate the aromatic ring so that we don't end up with a positively charged aromatic ring. That just doesn't make sense, Like you don't want to just stop here. So if you're in your mechanisms and you just stop there, that positive charge should just ring an alarm, okay? Remember that there's 2 resonance structures per carbocation, like 2 more, so in total 3. So watch out for that. AlCl4 is in a equilibrium with it goes back and forth, right, as we see right here, between AlCl3 and chlorine, right? So just in case you want to prove to yourself why we have this Cl- coming back to attack this hydrogen right here, right? That is possible because of this like equilibrium reaction going on, okay? So, like I said before, carbocations, they like to rearrange. So Friedel-Crafts alkylation can be altered with. It can go against what you expect just by that rearrangement. A great example is when you have a secondary or tertiary and then a hydride shift or so let me walk you through this. So a hydride shift would throw it off, but let me walk you through this. Like I said, we have let's say, so this is initially secondary, right? You get rid of the chlorine, and this results in a secondary carbocation. But then you notice that this could easily become tertiary if you just do a 1,2 hydride shift right here. That would result in a by the way, methyl shifts might also work, so you got to watch out for those too. But in this case, a hydride shift would result in a tertiary carbocation. So even though you use the right reagents, that carbocation rearrangement can throw off the whole synthesis. So this would result in a different product. So you got to watch out for that. You got to take that into account for when you're doing Friedel-Crafts alkylation. Another exception is when you have a primary reagent like so, and you think to yourself, okay, no carbocation is going to form because it's primary, right? But then a hydride shift can just completely undo your thinking and result in a secondary carbocation that is relatively more stable, right? And since this is possible, we are able to it essentially messes up all of your thinking, because the Friedel-Crafts alkylation that you initially thought might rearrange or shift, and it would result in a different product. So you got to really keep track of these things when you're using Friedel-Crafts. The next reaction we're going to be talking about is Friedel-Crafts acylation. It's where you use an acid chloride or anhydrides. Those are also acceptable, but Dr. King likes to use acid chlorides and AlCO3 with H2O. This results in the addition of an acyl group right here. Remember, this is the acid chloride I'm talking about. And so, once again, we're going to create the electrophile. We're going to attack with benzene and regenerate the aromatic ring. I'm just going to show you this mechanism right here. I don't want to go through it again because we're repeating the same 3 steps, right? That was a weird start. But I think the key thing that I like to remember about this reaction is that the acylium ion that is created from this electrophile, usually Dr. King likes to ask, she likes to ask like, which one's the best resonance structure? And the key thing about that is that you want to look at the number of bonds. So if she asks you, or any professor asks you, what's the best resonance structure out of the ones shown, you want to look for number of bonds. So since we have 3 bonds here, but then 4 bonds here, you know that this one is going to be your most favored or best resonance structure, because because the number of bonds in a resonance structure is most important. You can, if you notice that the bonds are equal in both, then you can look at charge. Then you can look at like where the charge is, electronegativity, and all that good stuff. But bonds allow you to kind of satisfy those octets and satisfy those octets and stabilize the resonance structure. Okay, so next thing. So we've talked about how to replace hydrogens and put on different substituents, but now you want to know how to like go from there. You need to know what's going to allow you to further react that ring with more substituents, like to further replace more hydrogens with another group. So there's 2 types. There's ring activating and deactivating substituents. Ring activating make the benzene more reactive or welcoming to new substituents in an ortho-para direction. Now, before I continue, we need to know what ortho-para and meta are. So let's say this is your substituent. This is ortho, right? Right next to it. That's how I think about it. Ortho. And then meta is right between ortho and para, right here. So, and this is on both sides of the ring, and then para is directly opposite to your substituent, okay? So it's kind of strange to think about, but meta is kind of the easiest one to think about because that's in the middle. Ortho, right? Para. So there you go. So strongly activating groups, they all have lone pairs, and except for the weakly activating groups right here, like the phenyl groups and the carbon chains or alkyl chains, right? Alkyl groups. Orthopara for activating, right? That results in a extremely stable resonance for carbocations. Thus, that makes it the most favorable. I could draw out all the resonance structures, but long story short, orthopara is the best. That results in the best resonance structures, and that's why ring activating substituents result in orthopara directed substitution. So yeah, so ring activating, it makes it more reactive, and the new substituents are added in an orthopara fashion. So they're either placed on the ortho carbon or the para, which is directly opposite, whereas ortho is right next to it. Ring deactivating are completely opposite. Basically, they make benzene less reactive or less welcoming, and they direct it in a meta fashion. And this is due to the stability of the resonance structures that it induces, and they are all they're all deactivating, and you can notice that they kind of have well, if you see a positive charge on anything like a nitro group or positively charged nitrogen, you know that's going to be deactivating, or anything with a partial positive, right? Anything with a partial positive, is going to be deactivating, right? And so from there, you can just kind of deduce that these things are going to be making it in a meta fashion or less welcoming to new substituents. So halogens are also slightly deactivating, but orthopara directing. So this is kind of counterintuitive to what we just talked about. They're deactivating because they have that partial uh, electronegativity, right? They're electron withdrawing. They're not partial, they're electronegative, right? So they're going to be pulling electrons away from the resonance structures, but they do contribute their lone pairs back into the ring. So it's kind of like a push and pull, pros and cons kind of situation where they're slightly deactivating because they're electronegative, but then they're donating their electron pairs into the ring of resonance structures. So that weak, albeit weak, but that extra resonance that they add allows it to be directing new substituents in an orthopara direction. So that's where it kind of gets weird, but just know that halogens add it in an orthopara fashion and they're slightly deactivating. When these substituents are being added, para is always favored, okay? Um, so, and this is regarding orthopara directors. So when we're talking about orthopara directors, since steric hindrance is always an issue, when you have a larger substituent where, like, for example, if you have methyl, it's kind of relatively small, so para is okay. It's not always going to be favored. My bad, this is ortho, let me correct that. Remember, this is para. So as the substituent gets larger, as we can see right here, the para position is going to be favored because of that steric hindrance preventing this substituent going here. However, it's not impossible, but it's just going to be in this situation, as this substituent gets larger, the para position is going to be favored. So if you have two or more conflicting substituents, you know that the strongly activating and orthopara directing is going to be the most important factor. So if you have a strongly with electron withdrawing and a strong electron donating group, you know that this guy is going to win, okay? So you know that it has electrons to donate, you know that it's going to donate those electrons, so it's electron donating group, it's activating, it's orthopara directing, and since para is favored, we're going to see the new substituent go in the para position, okay? So that's where you got to keep track of your substituents. You know how to add these substituents now, but now you have to keep track of how they interact with each other and how they impact the addition of new substituents. So there's some groups that are so strongly activating that it results in multiple halogenation. So we want to prevent that because sometimes you don't want the whole benzene to be covered in ortho and para bromines. So what you're going to do is you're just going to, for hydroxy groups, you're just gonna not put the catalyst FeBr3, and you can just do Br2 CCl4. Okay, that will allow monohalogenation, and that will result in some. I would still say para is favored, but ortho would also occur. But yeah, so since you can't like completely eliminate one or the other, it would just be like a flaw within your synthesis that I feel like most professors aren't going to like judge you too much, but just know that this is the key thing about this is that this results in monohalogenation, and if you don't do this, that will mean that you'll just have a bunch of bromines, and every possible ortho and para position will be brominated / chlorinated or just halogenated, right? Same thing for aniline derivatives. So you need to acylate them. So any amine substituent on the benzene will be highly activating. So if you want to just monohalogenate, you need to go through a slightly more complex process, but overall you're just making it moderately activating. So acylating the amine is going to be a common pattern that we're going to see to make it moderately activating. So you acylate with CH3Cl, so acyl chloride, right? Acid chloride. with pyridine. That results in an acyl group being attached to the amine. Then you use Br2FeBr3 to brominate, just like normal. But then you don't want that acyl group to stay attached to the nitrogen. So then you get rid of that acyl group by using H3O plus with H2O, followed by a separate step of NaOH, like so. That will result in a monohalogenation, and since this is such a bulky group, para is going to be favored. Right, para favored. So, Friedel-Crafts reactions, nor nitration can take place with aniline derivatives, so we must acylate beforehand, okay? So once again, something about aniline derivatives or this amine substituent prevents it from like normally working with reactions. So you need to, this is going to be a common pattern. So whenever you see this guy on your benzene, that's when you know, okay, I need to probably acylate this before I move on, okay? So you're going to use CH3C, you're going to use acid chloride with pyridine. Then you can go from there and add an acyl group or a nitro group, right? And then since right after you add those those respective substituents, right, whether it's a nitro group or your acyl group, you want to get rid of this acyl group that you've attached to the nitrogen of the amine, right? You want to get back to that aniline derivative, right? So then you just do H3O plus H2O followed by NaOH. Make sure to separate those into two separate steps. But yeah, so acylate the amine, you use acid chloride with pyridine, but then to get back to normal, you're going to use H3O plus, H2O, and NaOH in separate steps. Remember to do those in separate steps. That's another key thing. But in between these two steps, you just treat it like a business as usual, okay? You add your nitro group, you add your acyl group, whatever you want, okay? Remember to do this before nitration or Friedel-Crafts or monohalogenation. Okay, so there's 3 situations where you should be acylating your amine so that everything goes. So let's say you wanted to get a carboxylic acid, right, from a methyl group or any kind of alkyl group. So in order to do this, though, you must have a benzylic hydrogen. The benzylic hydrogen allows this reaction to occur, and without it, it won't work. Okay, so you must have a benzylic hydrogen that will then react with KMNO4, heat NaOH2, H2O, followed by H3O+. You need those 2 steps to be separate, right, or else it won't work. So yeah, I think that's the key thing that I like to take away. Is that it must have a benzylic hydrogen. The reagents, you kind of just, with practice, you'll memorize it and get it down. So when you have a substituent on benzene, you can also reduce it as well. So you can't have oxidation without reduction, guys. So let's talk about the reductions. So NO2 to NH2 via H2 palladium. That's just a common thing that you might see. That's another way to get an aniline derivative. Great way to do it in synthesis in like one nice step from nitro to NH2. You can also use zinc HCl followed by NaOH in 2 separate steps. When working with synthesis, you also have to keep track of the other functional groups within the compound. So if you have a carboxylic acid right here, but then you just care about this ketone, you want to do a Clemmensen reduction because the Clemmensen reduction won't affect these acids. It's great for acidic conditions and will only it'll reduce this ketone without affecting this carboxylic acid. So these 2 reactions, Wolff-Kishner, which I'm about to talk about, is only useful. It can only be used on ketones, aldehydes, or nitro groups. So do not use it on anything else aside from those 3 types of groups. So ketones, aldehydes, or nitro groups, okay? So when you're working with basic conditions, whether there's, just in case there's some sort of basic group within the rest of the compound, you can use Wolff-Kishner, in which you have H2N NH2 with NaOH. You would reduce this aldehyde to its methyl version, right? So once again, it only works with ketones, aldehydes, or nitro groups.